come to, well, sort of a laboratory of Professor Trethewey.
Welcome, student. How are you?
I am here reporting for today. Yeah.
Let's do a little primer.
Please.
A geothermal is just a heat pump.
Right.
The important thing about a heat pump is they all basically work the same. The only question is what is the source of the heat and what's the delivery method? So it's always going to be air to air, air to water, water to water, water to air. So the most common heat pump we know is air to air. You've seen the condensers outside. You'll see the high sidewall units. Often it's just got refrigerant piping between the two, and it either heats or it cools. End of story. Right?
And when you say air to air, that's because it's getting or dumping the heat from the air outside
Absolutely.
To condition the air inside.
We also see that you might have a unit outside that could be from multiple indoor units, and inside you might have something that almost looks like a furnace with ductwork that goes to the building, and then these high sidewall cassettes. There's no limit to the types of delivery methods inside, and they work fine. The issue is when it gets colder outside, these have to work harder and harder. You know, most of the year we want 70 degrees inside, and when it's 70 outside, there's no heat loss, and it's simple.
I could do that.
You could. We live here in the northeast corner of the United States, so it might get to be 100 degrees on a terrible day. We might get to be 0, or even we once in a while see -10 around here.
Right. Well, you can see why if you have to go from something like -10 to 70 degrees, that's 80 degrees you've got to make up, so you'd probably have to work really hard.
Correct. Now, down below the ground, after you go about 4 or 5 feet, it's about 50 degrees.
All the time.
All the time.
Every day.
Okay. So now, if that's the case, you could introduce a water to water or water to air geothermal heat pump. To tap into that constant 50-degree temperature, a series of wells would be drilled down several hundred feet. And there's a pump, and then this would come up here and go into the building right here. Now inside the building, it would be a lot different looking unit.
And so just so that I understand, going from 50 degrees to 70 degrees, moving that 20 degrees, is a lot easier than moving the 80 degrees here, so this is good.
And that's really the key to it, Kevin. We're trying to move heat. We're not trying to make it, we're trying to move it, and so we can find the 50 and easily pump that thing up to get the building to 70.
Gotcha.
The piping runs into this water-to-water geothermal condensing unit, which gives us a lot of advantages. We want the system to be able to heat and cool different parts of the building at the very same time.
Right.
So for that, we're going to introduce 2 tanks. One's a hot tank, one's a cold tank.
Storage tanks, essentially.
Absolutely. So now what happens is you can send heated water up to the coil in the air handler right here. So too on the cold water side. And it goes up here.
Mm-hmm. And when I compare an air source heat pump to a ground source heat pump, we like this one better, is more efficient, less efficient?
They both will work on the coldest day of the year. It's when you start talking about efficiencies in colder weather. As this chart shows, when the outdoor temperature drops, the air source heat pumps have to work a lot harder to reach the desired indoor temperature, while the geothermal system remains at its high efficiency, because you're not subject to the vagaries of changes of outdoor temperature.
So now you've made the house comfortable.
Yep.
Thank you for that. I still want to take a shower or run the dishwasher. Where do I get my hot water from?
Well, this beautiful buffer tank, the storage tank storing BTUs, we've ordered it with a heat exchanger inside it, so that we're going to take some heat off of the heat pump through this coil. Potable water will come through here, and now that's going to be hot enough to make the faucets hot enough. But we also have there's all these pumps and all the equipment. So in the mechanical room, there's always temperature, in here. So now what we're going to do is add the last component, which is a heat pump water heater that will find the heat that's in that air, transfer it down into this tank, which will act as a reserve tank and help in the production of domestic hot water.
Wow. And so the equipment is what we're looking at here?
Here's our lineup. Here's our geothermal heat pump. This is one of 2 that we'll have in the building. For simplicity, I just have the one. Compressor, expansion valve, reversing valve inside here. You can see there's tappings right here. This goes out to our wells down, and it could go 400 or 500 feet. This goes to our piping inside the building, to our load. Now that'll come up to the radiant, but also will go to air handlers. This is a really smart blower that can spin at different speeds, coming out through the ductwork. Here's the cooling coil. Chilled water will go through this coil back and forth. Air will be drawn across it, and in cooling mode, it'll take heat out of the air, thereby cooling the air. Anytime you air condition or chill the air, there's going to be condensate, so there's a condensate drain for that. Here's the hot water coil right here. So air, turn on the thermostat in this zone, air gets drawn in through the hot water coil. The decision is made between heating and cooling. The air comes out at the right temperature here.
Yep.
And every part of the building can be individually zoned.
And then your BTU.
2 tanks, a big blue tank and a big red tank. There won't be, but one's the buffer tank hold. They both look very similar. But the hot water tank's going to have an additional piece I mentioned. This is the heat exchanger inside of it. So now, this stores all this BTUs ready to go for the heating, but it also has a coils inside of it that potable water will come through here, and it'll now come out heated. And now that last step is you got all that heat in the mechanical room. This heat pump comes on, pulls that heated air in, transfers again through that same refrigeration cycle that's in every heat pump, transfers it down to the tank. So we haven't wasted any energy anywhere along the line.
Sounds super efficient. Why don't we see them all of the time?
Well, I think it's the first cost. I mean, this is a fair amount of equipment. It has to be installed right. It has to be done professionally. It has to be sized right. It has to be done generally by an engineer. I happen to know a really good engineer, so I could offer him to you.
If you could get him to our house, that would be terrific.
Right.
Awesome. Thank you, Professor.
All right, brother.
Is there going to be a test?
No test for you. Thanks.
So Ross, you're the engineer on this project for our heating and cooling. Where do you start when you're designing a system like this?
After doing the energy model, which takes into account things like square footage and insulation, I engineered a geothermal system that will efficiently heat and cool the home. As a reminder, no matter what the air temperature is outside, once you get around 20 feet below the surface, it's always about 50 degrees. In order to tap into that constant temperature here at this project, we need to drill 4 wells down to a depth of 500 feet each and 20 feet apart. That spacing is important to minimize the thermal interference from one well to another. And today, we're going to start drilling.
Well, here's a drill bit very similar to what we're going to be using.
That's right. So most people think it's like a screw, like an auger, but in fact, it's actually pulverizing the rock. So it's actually hitting it about 30 times every second. And as it's doing that, it pulverizes the rock and spins at a slow rate to move through the earth.
And on this end, a water-air mixture goes through
That's right.
and comes out these ports here.
That's right there. Yep. And so it's going to move that pulverized rock up to the surface, keep the dust down, keep the drill bit nice and cool.
In this town, we have to be a minimum of 25 feet from the street and 10 feet in off the property line. And that lines up perfectly to put the wells right here.
Right here, 4 in a row. The tungsten carbide drill head is attached to a 20-foot shaft. Once it drilled down that 20 feet, another 20-foot shaft gets added to the stack and the drilling continues. Here at the site, we are drilling through layers of soil and then into bedrock. To prevent the soil portion of the well from caving in, they insert a steel casing to hold its shape. Once we hit bedrock, we don't need to add any casing because the bedrock itself creates its own borehole. Later, a loop of high-density polyethylene pipe filled with antifreeze and water will be inserted into each hole. Then they'll pump in a grout mixture to completely encase the loop of pipe. That grout will help conduct the heat between the earth and the loop pipe. In the warm weather, the geothermal heat pump uses that constant 50-degree temperature to cool down the loop pipe and warm it up in the winter.
My calculation is only 470 feet to go.
And 3 more wells.
Well, let's get them going.
Alrighty.
Thanks for watching. This Old House has got a video for just about every home improvement project, so be sure to check out the others. And if you like what you see, click on the subscribe button to make sure that you get our newest videos right in your feed.